Friends, if I talk about solar photovoltaic technology, then in this, solar cells absorbs the sunlight and convert this light into electricity. While this current is direct in nature, that is direct current, the inverter attached converts this direct current into alternating current and run our electrical appliances. So this is the basic functioning of solar photovoltaic technology. Sunlight is effectively converted into electricity using solar photovoltaic cells, which are traditional silicon-based solar cells. These are widely utilized around the world, but at the same time, significant developments in photovoltaic technologies are being made, and we can see new technologies are emerging out. And one of these technologies is Tandem Solar Cell Technology. But before learning this, let us go back into a bit of history. In 1961, way back in 1961, two scientists, Shockley and Cuser, they made very interesting discovery about the solar cell. They found that the single junction solar cell, single junction, I mean to say, when p-type and n-type are stacked together, combined together, we get one p-n junction, and that solar cell would be called as single junction solar cell. Okay, in that single junction solar cell, the maximum efficiency achieved is 33.7%. Or in other words, I would say that no single junction solar cell would cross the efficiency of 33.7%. This is the theoretical efficiency. Well, if you take any solar cell having a single junction, its efficiency will not be more than 33.7%. Moreover, the most efficient band gap is 1.34 electron volt. And what does this mean? It means that a solar cell which has a band gap of 1.34 electron volt would have a maximum efficiency of 33.7%. Any other solar cell which has a band gap different from 1.34 electron volt will have lower efficiency than 33.7%. So what exactly is band gap? Band gap, it's the minimum amount of energy that is required by the valence electrons to jump up and go into the conduction band and start conducting. So minimum amount of energy that I should provide to the electrons rotating or circulating in the balanced band to get excited enough to jump to the conduction band and start conducting. So this minimum energy is represented in terms of electron volts or in band gap. So the ideal most efficient band gap for any single junction solar cell is 1.34 electron volt. So if a solar cell is having a band gap of 1.34 electron volt, then it has the maximum chances to achieve the theoretical efficiency of 33.7%. And any other solar cell which has a band gap different from this will have efficiency obviously below 33.7%. Now the question is, why do we use silicon in photovoltaics? We could have used another kind of solar cells also, but why silicon solar cells, silicon-based solar panels are abundantly used around the world? First reason is it is durable, it is available, and another reason, the another major factor is it has a band gap of 1.1 electron volt, which is very much close to the ideal band gap. And because of this, silicon can efficiently convert sunlight into electricity. Let me explain it through diagrammatically. Let's say a solar cell which has an ideal band gap of 1.34 electron volt can achieve the maximum efficiency of 33.7%. Any other solar cell which has band gap other than 1.34 electron volts will have efficiency below this 33.7%. It is a silicon which has a band gap very close to the most efficient band gap of 1.34 electron volt. It is because of this feature, apart from its durability and availability, silicon is one of the best solar cells which is being used for making solar panels. So this was Shockley-Cuser limit. The finding was very much interesting. This limited the maximum efficiency of solar cells to 33.7%. But with the advancement in technologies, new technologies are emerging out, and yes, obviously, with tandem solar cell technology, we can cross this limit and we can have efficiencies beyond 32.7%. And how this is possible? Tandem solar cells has the capacity, have the capacity to cross over 30% power conversion efficiency and are expected to significantly contribute to the required shift towards renewable energy. But how is this possible? How we can achieve efficiency beyond the limit specified by Shockley and Cursor of 33.7%? It is possible when we have multiple solar junctions. What I mean to say, when we stack together two or more solar cells with varying band gaps, this configuration would enable us to absorb more broader spectrum of light or photons, thereby enhancing the overall efficiency of the solar cell. Let me explain you in detail. When two different types of solar cells are paired together, assuming I have two solar cells, one is perovskite solar cell and another is our traditional crystalline silicon solar cells. We will discuss why we are using perovskite solar cells. When these two cells are stacked over one another, silicon being at the below of the stacked, we can improve the overall efficiency of the solar cell. This tandem configuration involves stacking the two solar cells with the perovskite cell positioned on the top. The perovskite solar cell is designed to be semi-transparent, which is effectively converting high-energy photons into electricity. And this perovskite solar cell, it passes through the low-energy photons through the crystalline silicon. And crystalline silicon absorb low-energy photons and convert it into electricity. This innovative stacking approach allows for greater proportion of light to be converted into electricity, thereby maximizing the system's efficiency. Let us understand through diagram. We have two cells stacked together, top cell made up of perovskite solar cell and the bottom cell is crystalline silicon cell, our traditional solar cells. When these two are stick together, we are going to have improved efficiency. Let us understand through this diagram. Sun shines, it gives you electromagnetic spectrum. Electromagnetic spectrum, it consists of photons of different energy from high energy to low energy. While the top cell, which is perovskite solar cells, are designed to absorb. The interesting part of perovskite is that they are tuned to absorb desirable frequencies. The perovskite solar cell absorb the higher frequency of light. You can see that. Out of this complete spectrum, perovskite solar cell absorb the higher frequency photons and let lower frequency photons pass through this and made it available to the bottom cell, which is made up of silicon. So in this way, because these two cells are having different band gaps, perovskite solar cell has a band gap which is capable of absorbing higher energy photons, while on the other hand, silicon cell, the bottom cell, is configured to absorb lower frequency photons or lower energy photons. And this configuration allows to absorb the wide spectrum of the light, hence improve the overall efficiency of the cell. By pairing with perovskites, we could have paired with another kind of solar cells. We know that silicon-based solar cells mainly convert longer wavelengths or low energy photons into electricity. While on the other hand, perovskites, which is basically of structure AbX3, AB is positive cation, B is positive cation, big and small respectively, and X is the halide. By varying the constituents, by varying the proportion of halides, we can actually tune the perovskite to absorb the desired frequency of light or to absorb the desired energy of photons. So by adjusting the ratios of material used to create perovskites, they can produce a variant that has the particular color and absorb specific wavelengths of light. So because of their ability to be tuned to different wavelengths, they are used for tandem cell technology. Let us understand it more clearly. This is the visible spectrum. You can see that the perovskite layer in the solar cell utilizes the full visible spectrum, that is from 380 nanometer to 700 nanometer, starting from this 380 nanometer to 700 nanometer. While on the other hand, and they absorb this range of wavelength and generate electric current. While near infrared light, that is from 800 nanometer to 2500 nanometer, it penetrates and energizes the underlying silicon cell. Together, this combination boosts power conversion efficiency to over 30% with a theoretical potential of 40%. So while on one hand, perovskites are tuned to absorb higher energy photons, silicon cell absorb low energy photons. In this way, together, when they are stacked together, they absorb wide range of photon energy and convert it into electricity, hence improved efficiency. Let us understand tandem solar cell structure. This is front transparent electrode. Perovskite solar cell and silicon solar cell are stacked together through a tunnel junction, which allows electromagnetic waves to, or which allows lower energy photons to pass through silicon solar cell. The front transparent electrode allows light to pass through effectively into the perovskite solar cell. Perovskite solar cell absorb high energy photons and seeps through the low energy photons through tunnel junction into the silicon solar cell. Silicon solar cells convert low energy photon into electricity through the back contact, and we get load running. So in this way, tandem solar cell structure absorb wide spectrum of energy and convert it into electricity. Well, even though tandem solar cells are very efficient, we have problems associated with tandem solar cells. Now let us discuss the problems which are associated with tandem solar cells. First one is cost efficiency. One of the major problems that are associated with tandem solar cells is the cost. Even though they are very efficient, you can have efficiencies over 30%, but they are costly. Because of this, the production line, the making of stacking two cells together required two cells, I mean to say perovskites and silicon cell together require a complex production line. And this complex production line requires heavy investment. So one of the problems with tandem solar cell technology is their cost. Second one is mechanical compatibility. That is compatibility, which includes mechanical compatibility and electrical compatibility. See, we are sticking two cells of different materials together, and these two different materials must stack together effectively without cracking, even when subject to different variations, temperature variations. We can easily understand that when two different materials are stacked together, with the change in temperature, their expansion, contraction, they would have different expansion and contractions because of their different material nature. So it is a challenge to the manufacturers that how to make two solar cells stacked together without cracking when subject to temperature variations. Another is electrical compatibility. We have discussed that the top layer absorbs, that is the top cell absorbs the higher energy photon and lets low energy photon pass through and being absorbed by silicon cells. This whole configuration has to be effective enough to work in tandem. The upper cell must be capable of absorbing a portion of light to generate electricity, while the remaining transparent enough to allow light transmission to the lower cell for absorption. It could be possible that no amount of light pass through the bottom of the cell. Or on other hand, it could be possible that high energy photons may pass through the top cell without being converted into electricity. So therefore, electrical compatibility has to be maintained with the mechanical compatibility. Another problem is durability. Well, it makes little sense in developing a tandem cell in which one of the cells will stop working after a fraction of time during the lifetime of other cell. Well, if I tell you silicon, yes, the one of the reasons that we have discussed why silicon solar cells, why silicon solar panels are being used worldwide abundantly because of their durability. Silicon cells, silicon solar panels have a lifespan of over 25 years. While on the other hand, perovskite solar cells, they have very, very limited time period, lifespan, useful lifespan of around 1 year or even less than that. This is fraction of what we see in silicon solar cells. 25 years in case of silicon solar cells, in less than 1 year in case of perovskite solar cell. These perovskites solar cell, when exposed to sunlight, they undergo oxidation. They very quickly, they degrade, they deteriorate very fast. That is why they lose their functionality over a period of time with a very short span of time. So if we see the difference of durability, I can say that silicon solar cells are 25 times more durable than perovskite solar cell. So it makes little sense of pasting a thin layer of perovskite solar cell over the silicon cell if this layer is going to degrade in less than 1 year. So why one should invest a huge cost in developing a perovskite tandem solar cells? So durability is also one of the major concerns for the manufacturers, scientists, and the engineers equally. But despite these challenges, the South Korean company QCells has launched the production line for perovskite silicon tandem solar cells, which could enhance efficiency by 50 to 75% compared to standard solar panels. We know that traditional silicon solar panels have the maximum efficiency of around 22%. If you look at the recent news, we see maximum efficient solar panels have an efficiency of around 22-23%. But by using tandem solar cell technology, this efficiency of 22-23% can be increased by another 50%, minimum of 50%, and we can raise it to 33%. So looking at this possibility, QCells has invested or is investing $100 million to the transition this technology from research to production. And this is indicating that tandem solar cell technology may become widely used in the coming years. More and more companies would be coming to set up their production lines for tandem solar cell technology. So friend, this was all about tandem solar cell technology. Thank you.